So, you guys want to know the good news or the bad news?
Bad news first.
Bad news. The bad news is we're about to go into the most complex subject in operating systems. It's so complex because there's so many pieces. The good news is we're going to go through it slowly. We're going to take 2 full weeks. We used to take 1 week to do this. Okay? And just the fact that there's so many moving parts, I think it's very hard to sort of assimilate all that and then ask questions that are meaningful to you. Okay? So this is kind of my way of saying that it's going to be really, really hard. You're being too hard on yourself if you don't do the reading before you come to class. Because it's not enough that it makes sense, it's that it makes sense to you long enough for you to use the material. That is for at least the next 4.5 weeks, right? So there's lots of little pieces that's all set up to be highly interactive. Ask lots of questions. If we don't have any questions, well, I already know the stuff. So it's not going to hurt me. I would really prefer that everybody ask lots and lots of questions. But if we don't ask questions, I'll be happy to end early. But I don't think that's to your advantage. So we're going to go now into the topic of virtual memory. Virtual memory is really quite cool. I mean, it's one of the great inventions that we have. I hope to have this fixed by the weekend, but I want to point out that currently there's a mixed style of diagrams in here because I didn't have a chance to redraw all the diagrams, but I'll get them drawn in the next few days. Okay, so we're going to go into this topic progressively, and just like we did with scheduling, it's going to look historical, but all these looks that we have, which look at using pure physical memory without using virtual memory, we'll look at address translation, what does it mean to have virtual memory, then we'll move into segmentation, and then finally we'll move into paging. We'll take a look at a bunch of algorithms along the way. All physical and segmentation and paging are all approaches that are used today. So it's good for us to understand both the strengths and weaknesses of the different approaches and ask ourselves an interesting question. Is it worth it? Okay. As we go through here, we're going to find, we saw this with scheduling as well, is that as we go through, we're going to get more complex algorithms. And complex algorithm says what about our latency? It goes up, doesn't it? So, in order for it to be useful, it has to have some benefit that outweighs the delay or latency of the algorithm, right? Sneak peek, the answer is yes. All the way around. Okay. So, physical memory is usually what we think of when we see a memory stick like this. This is a DIMM. Does anybody know what the difference between a DIMM and a SIMM is? In general? How can you tell them apart?
Dual versus single something? Is that what they
Dual versus single something, so there's a D and an S going on there.
So there's twice as much.
Twice as much. Well, as it turns out, it's even weirder than that. Dual means there's chips on both sides. Single means it's just chip surface mount on the other side. This is an advance in surface mount technology. But it's really, really cool. Okay? It's really cool. And so this is what it kind of sort of looks like. And when we talk about physical memory, to a lot of people, this is what they think about. The memory sticks that I can touch. That's really not what we mean in this class. Yes, it's these chips, but how do we access them? What do they look like to the operating system? Does anybody know what it looks like to the operating system when we plug these guys in? An array. Okay? It's an array, and depending upon where these are at in our insertion order, there will be a contiguous block of addresses that relate directly to the memory locations on this chip. And memory we address how?
Pointers.
Pointers, but the addresses are words. Do we point to words? Numbers? Let's phrase it a different way. Memory is what addressable? Word addressable? It's byte is our smallest. We normally get things, a lot of the time, we get things in word size, architectural word size. But memory is byte addressable. Okay? The interesting thing about that, of course, is that we can't access individual bits just by reading memory. We have to get a block of the bits, and then we have to shuffle them around or do something like that. Do you guys remember masking, bit shifting, all that fun stuff from 201? Okay. How many of you did the fake IEEE floating point exercise? Anybody do that? How many of you are just having bad memories now? And the rest of you are going like, hey, I want to go off and do this, and the rest of you are going, no! Lots and lots of bit manipulation there. So we're going to view memory as just an array of bytes. Okay. Physical memory just goes from 0 to however many bytes of memory you have. Virtual memory, we get to it, it turns out it goes from 0 to some number, and it has nothing to do with the amount of physical memory that you have. They're completely different. So, I thought I'd put in here, I took this from a Wikipedia page. It says, oh, DIMMs became the dominant type about the time the P5 Pentium processor showed up. Was anybody alive when the P5 Pentium processor showed up? Okay. Were any of you awake? No. I wasn't, certainly. That's before even the Pentium Pro. So that P5-based Pentium, I believe, is the one that couldn't actually, didn't actually have a single value for 2. Remember the problem when it was like the square root of 4 was 1.999999999 or something like that, and then it just didn't do round correctly. So, when we're directly accessing physical memory, there's some things that we need to keep in mind. Okay? And having been an OS developer, where I worked through both virtual memory and physical memory, I just want to kind of give you my perspective on accessing physical memory directly. And that is, don't do it if you don't have to. Okay? The reason is the following. When you have access to bare metal, which is what this is, we're having access directly to the device itself with no intervention anywhere. When we're programming bare metal, we can do anything we want. In fact, we saw that with the CPU. If we were using the real CPU, we could turn off interrupts and just stay in that processor all day long, couldn't we? Okay. In memory, it means that we can access any memory location. All right. Which means there's no protection, there's no security. We have to have isolation. And physical memory, when we can access it directly, does not. Interestingly, the operating system can access physical memory directly without going through virtual memory. It can do that. But it's trusted, just like it is on the schedulers, right? In fact, it's going to give us the virtual memory illusion, which will solve this protection and isolation problem. Okay? So, what do you guys think? If I was running in a system that had multi-programming, so I had lots of processes in memory, so there's lots of data for other processes that are out there. And I have my little program running, and maybe it's balancing my checkbook. But I just happen to know that the software for balancing accounts at my bank also runs on my machine. Could there be an opportunity there for me? Or at least a temptation? Okay, it turns out if I'm running directly with physical memory, the bank can't stop me from accessing that memory. There's other things it could do cryptographically, all right, but it's kind of odd. Like, why would we want to let a group of processes actually interfere with each other? And we're not really trying to allow that. What we're doing in the days back before we had virtual memory that was all we had. This was as advanced as we had gotten. Okay. Nowadays, if we're going to use pure physical memory and not use virtual memory, the reason is typically because we need the speed, or the overhead of virtual memory is just not very useful. Okay. We really don't need to give a 2 gigabyte virtual process space to our hearing aid. Okay. Typically, something like that is going to access physical memory directly. Okay. A lot of embedded systems use physical memory. A lot of current embedded systems that are being developed, particularly for Internet of Things, however, are typically running Linux or RTOS or something like that, where they are using virtual memory. So it's becoming a mix, primarily because processors are becoming smaller, faster, cheaper. Okay. So I have, 2002 or 2003, I actually had a bunch of network cards from Intel, and they had a P6 processor core, but essentially the equivalent of a Core i5 sitting on the network card, and it ran full Linux, and you could log into it remotely. All right, and it was really cool because there's lots of stuff you could do down at the network card level, and it made a lot of sense to do that. Okay, it was kind of fun because, of course, you know, I'm just doing research, so I'm not hammering it. But these types of very intelligent cards are being used in switches, routers, telephone systems, things like that. Lots and lots of memory. I think we had 1 gigabyte of physical memory. This was 15 years ago. Things like that. How many of you have seen an apple pie of some kind? Okay, that little $5 apple, that's not apple pie. Raspberry Pi.
Yeah.
How many of you have eaten Raspberry Pi? No. And saw an apple pie? No. So I was starting to bring my phone out, and I realized that wasn't the example. You should have just laughed at me, and I would have eventually figured it out. Sorry. So the Raspberry Pi has, if you look at the CPU, there's a little wafer, a little thin thing glued to the top of the CPU. And that is not its heat sink, that's 1 gigabyte of memory. Okay? About twice the size of your thumbnail. All right? So these things are starting to show up. And where we do certain types of embedded systems, so you guys, anyone in the Rocketry Club? shooting rockets into space with Professor Massey. Things like that are going to use physical memory directly. And it's really rather cool, but you have to be aware of the problems. Okay? The first one is, in some sense, just to sort of say it this way, you are your own worst enemy. Because programming bugs can pretty much go anywhere. How many of you have ever dereferenced a null pointer? I have. Okay. In physical memory, you can dereference null pointers and it's not an error. Think about that. And in a lot of systems, what lives of address 0 is the operating system. So you have a bug in your program and you crash the operating system. Is it obvious to you that you have a bug in your program? Okay. Maybe it's a test program testing your operating system. So now you're testing both the test program and the operating system. And where's the bug? Okay. In that particular case, it's probably not the operating system. It's probably the test program. It chased a null pointer. Okay. You do not have this type of protection. The way we like to draw it is we say the CPU directly accesses memory. I want you to notice something. Okay. The term I use is emit. So the CPU, when it goes to access memory, it uses physical addresses. Which means that the linker must provide physical addresses. Okay, you can get the linker to do that. Some linker switches for that. And we go out to address X, and if we happen to be a 32-bit machine, we'll bring in X through X plus 3, right? Or 32 bits. Or if these are 32-bit wides, we might just bring in X. So now, we look at that, there's no opportunity for us to insert into this drawing. There's no easy way for us to insert in there things like protection from bugs. Isolation. Okay. Do we want processes to be able to read through all the kernel data structures? Okay. Things like this. Turns out in a general system, we kind of don't want that. All right? If you're sitting on Babbage or Ada, right? And if your process had access to every other process, would anybody be tempted if they had a bug to see if anybody code worked differently? Okay. You might. That'd be cheating. We prefer you didn't do that. But how many of you would mess with your friends? Go over and remove something from the ready list. You don't have to hold the lock. Just detect that the lock was just gotten, and then just go in and just mess with everything. You'd be like, I don't know, periodically a sleeping process is on my ready list. I don't know, but it's only when Mark's processes are running on the computer. I don't know what's happening. Think about that. This is really kind of ugly. Another thing that shows up is if we have a bunch of processes on our systems, what if the process needs more memory? What if it needs more memory, so we're going to try to grow the process, but there's another process right next to it, so it can't just expand where it's at. We're going to have to pick that process up and relocate it somewhere else in memory. When we're accessing physical memory, we know where we're supposed to be in physical memory. It's typically compiled in or read from a configuration card. Okay? In the early days, all the addresses were compiled in. If we needed to move our process, it turned out we couldn't do that while it was running, because all the addresses were physical memory addresses, And to go through and do what's called a fix-up, that is change all of those addresses to new addresses where we put you, it's going to take so long that it's just not worth it. So if you run out of space, you get to go to the people that own the system, ask for a bigger memory location, and they'll tell you what the address range is, and then you get to recompile your program. Okay? Sound like fun? Okay? Not a lot of fun. So we have this issue around relocation. You know, relocation is very, very important to us. We need to be able to move things around in memory. And physical memory, when we move something, it becomes obvious to the process. If the operating system could intervene, then we might be able to set it up so that if we relocate your process, or even just a part of your process couldn't tell. And this is one of the motivators for virtual memory, is that when we use physical memory directly, anything we need to do in order to manage, almost anything we need to do in order to manage the memory subsystem becomes visible to the processes. And like with the virtual CPU, what we want to do is hide that. We want to hide the fact that there are other processes on the system. Okay? In fact, your program only knows that there's an operating system when you make system calls, right? Think about that. If you make C library calls, then you know there's a C library. But you knew that if you're running in C, right? So you can't really say what are the contents of the kernel's memory. You don't have access to that with virtual memory. With physical memory, you do. Okay. So we set up here for our programming model. The process has to know